The generative AI boom was built almost entirely on the back of the graphics processing unit, or GPU. Because these chips function as a massive, flexible Swiss Army knife for computations, researchers found them perfectly adapted for the chaotic, trial-and-error process of training large language models. But the industry is moving past the laboratory phase. Today, the vast majority of AI compute cycles are dedicated to inference, the daily, repetitive processing of millions of live user queries across search engines and enterprise software. Using a highly generalized 700-watt GPU to run these repetitive inference tasks creates a severe architectural mismatch. It is the computational equivalent of using a heavy-duty pickup truck to deliver a single envelope, firing up a massive footprint of silicon components just to process a highly specific math problem. Multiplying that wasted energy across a global scale pushes hyperscale data centers directly into hard physical power constraints and rapidly deteriorating unit economics. To make matters worse, relying on merchant silicon means paying a steep premium. Nvidia commands gross margins exceeding 70%, imposing a massive financial tax on any cloud provider trying to build out inference capacity. This chart details the exact hardware economics per equivalent unit of compute. While a standard Nvidia H100 costs an estimated $21,000, an internally developed chip like Google's Tensor Processing Unit, or TPU, drops that hardware cost to just under $7,000. This diagram illustrates the shift. Merchant GPUs remain locked in foundational training. Meanwhile, hyperscalers route inference workloads to custom ASICs. By stripping away generalized pipelines, ASICs optimize the silicon for exact operations, slashing power consumption by 65%, drastically lowering total cost of ownership. For the world's largest tech companies, the shift to rigid, specialized silicon has become a strict economic survival mandate to bypass the physical scaling limits of artificial intelligence. But a critical vulnerability remains. A cloud provider like Meta or Amazon employs thousands of world-class software engineers who write incredible AI algorithms, yet they lack the capability to physically map 100 billion microscopic transistors onto a piece of silicon. Designing custom chips requires deep, atomic-level engineering expertise to interact with the cutting-edge manufacturing equipment at foundries like TSMC, the Taiwan Semiconductor Manufacturing Company. To bridge the chasm between their theoretical software ambitions and the harsh physical realities of foundry manufacturing, these cloud giants rely on a highly specialized translation layer, Marvell technology. This capability matrix outlines Marvell's exact placement in the supply chain. While the hyperscaler defines the algorithmic architecture, Marvell provides the custom IP blocks and the physical layout, supplying the critical components that cloud giants simply cannot build internally. Without this specialized middleman executing the physical architecture and managing the foundry relationship, the hyperscaler's multi-billion-dollar custom silicon ambitions would stall out in the design phase. Marvell operates as an intellectual property co-investor for these tech giants, supplying the complex surround silicon that allows the core AI processor to actually function inside a server rack. At the top of that list is SerDes, which stands for Serializer-Deserializer. This technology acts as the vital vascular system of the chip, rapidly compressing and pushing massive amounts of data on and off the processor at blistering speeds, without overwhelming the physical pins. Moving data across a massive AI cluster often consumes more power than the actual computing. By integrating advanced optical interconnects, a technology pipeline heavily bolstered by their acquisition of Inphi, Marvell solves the severe data movement bottlenecks crippling modern data centers. Marvell also manages the immensely complex physical packaging required to stitch multiple distinct silicon dies, or chiplets, together into a cohesive 2.5D or 3D structure. The hyperscaler writes the core mathematical logic for their specific AI model, and Marvell physically wraps that logic inside their proprietary power-optimized connectivity IP. They are engineering the foundational vascular infrastructure that guarantees the custom chip can actually communicate with the tens of thousands of other processors inside an AI factory. The financial mechanics behind this arrangement are incredibly lucrative. Developing a single AI accelerator on a leading-edge 3-nanometer process node requires hundreds of specialized engineers and easily costs hundreds of millions of dollars in upfront research and development. Marvell bypasses this capital risk by charging non-recurring engineering, or NRE, fees directly to the hyperscaler before work begins. The cloud provider underwrites the entire R&D process. Once the design is completed, it unlocks a continuous pipeline of volume production revenue. When the custom chip is finally validated and enters high-volume manufacturing, the financial model flips to highly predictable per-unit hardware sales backed by firm, multi-year purchase orders, carrying almost zero inventory risk. This specialized funding structure completely shields the company from the notorious boom and bust cycles of the broader semiconductor market, securing massive operating leverage and cash flow visibility. Once these custom chips enter high-volume production, the hyperscalers fall into a highly lucrative trap: multi-generational hardware stickiness. Because Marvell's proprietary networking interfaces and optical controllers are physically etched into the silicon at the atomic level, a cloud provider cannot easily switch vendors. Doing so would break their entire data center architecture and require rewriting years of customized software infrastructure. This chart forecasts the macroeconomic result of that lock-in, projecting Marvell's data center market reaching $94 billion by 2028. The custom compute segment alone expands at a 45% compound annual growth rate, driven by an active pipeline of dozens of unique chips. While Nvidia fights a highly public battle to maintain its grip on the experimental AI training era, Marvell has quietly capitalized on the hyperscalers' escape attempt, building an inescapable, multi-generational tollbooth for the high-volume future of artificial intelligence.